Periodic Properties 2. This video will cover the periodic property ionization energy. Ionization energy is defined as the energy that must be added to remove an electron from a neutral atom. The electron is removed from the valence shell first, not necessarily from the last subshell filled. This is because the valence shell electrons are further away from the nucleus than the inner electrons, and so are easier to remove. When we add that energy and remove the electron, we are left with a 1+ ion. It is possible to remove more than one electron from an atom, so what we call the ionization energy is also sometimes called the first ionization energy. The second ionization energy is the energy it takes to remove the second electron, forming a 2+ ion, and the third ionization energy is the energy it takes to remove the third electron, leaving a 3+ ion, and so on. There is useful information that can be found from looking at the further ionization energies of an element, but we will focus on the first ionization energy, or what we will simply call the ionization energy. What we see here is a graph of the ionization energy graphed against the atomic number of the element. As we look at the graph, we see an interesting pattern that is related to the rows of the periodic table. Row 1 contains just hydrogen and helium. Row 2 runs from lithium to neon. Row 3 from sodium to argon. Row 4 from potassium to krypton. And row 5 from rubidium to xenon. What we find is that the ionization energy seems to increase as we go across a row in the periodic table from left to right. The reason for this is that there are more protons in the nucleus toward the right. More protons attract the electrons more strongly, making it harder to pull an electron away. The ionization energy decreases as we come down a column in the periodic table. If we look at the noble gases, helium, neon, argon, krypton, and xenon, we see that the ionization energy decreases from helium to xenon. Looking at the alkali metals, we see the same pattern from lithium through rubidium. For the column headed by nitrogen, phosphorus, arsenic, and antimony, we see the same kind of pattern. There's also a reason for this pattern. As we come down a column, the valence shell has higher and higher energy, and the electrons are further away from the nucleus, so it requires less and less energy to pull an electron away from the nucleus. You should notice that the reason for the general trend across a row and for the general trend down a column is exactly the same as the reason for the trends in atomic radius. The effect, however, is exactly the opposite for the two properties. There are exceptions to the general pattern, however, and this time these exceptions seem to be regular. If we look at the elements in group 13, boron, aluminum, gallium, and indium, we see that the element in group 13 has a much lower ionization energy than the element immediately before it, beryllium, magnesium, zinc, and cadmium. This pattern holds for thallium and mercury. Why is there an exception here? If we look at the electron configurations of the group 12 and group 2 elements, we see that each has a valence configuration of S2. The elements in group 13 all have S2 and P1. The electron we are removing from the group 13 elements is in a higher energy subshell than the one we are removing from the others, so it requires less energy to remove, and the ionization energy is lower. You should note that this exception to the pattern is only for the element in group 13 and the element immediately before it in the same row. There is no exception for elements that follow group 13 or for other elements before group 13. The elements in group 16, oxygen, sulfur, selenium, and tellurium, also seem to be an exception compared to group 15, but not completely. Why is this? In both groups, the last subshell is a P subshell. Group 15 has a P3 configuration, and group 16 has a P4 configuration. So why are they an exception? The key is not the configuration, but the orbital filling diagram. The orbital filling diagram for group 15 looks like this, while the orbital filling diagram for group 16 looks like this. Group 16 has one orbital with paired electrons. Since the electrons repel each other, we get a bit of help when removing the electron from group 16, so the ionization energy is not as large as we would expect it to be. Notice, however, that for antimony and tellurium, there is not really an exception, and the exception becomes less and less as we go down the column. Why is this? As we come down the column, the orbitals get bigger. This means that the electrons do not need to be as close to each other further down in the table, and there is not as much repulsion. Again, you should note that the exception only applies to the element in group 16 and the element immediately before it in the same row. So, the ionization energy tends to increase across a row toward the right and up a column, with exceptions going across a row at groups 13 and 16. Remember that the exceptions only apply to the element in the group and the element immediately before it in the same row.